An electrolysis reaction is when electricity is used to cause or initiate a chemical reaction. And so what I've done is I've broken down electrolysis reactions into three different kind of categories so that we can go through and teach you what are some different types and how you can figure out what's going to happen when. So we've been running current through this copper bromide solution for a while. This side you're seeing bromine form, and you can tell just barely when I take this out that there's a discoloration, and that's actually the orange bromine is in there, and that's forming kind of a yellowish color which kind of mixes with the blue to form a greenish kind of hue. The other end I'm producing copper metal, and you can see this if I take this out and bring it right up close, that there's copper right on the teeth of that. And so the teeth of that now are turning into copper metal, or copper metal is plating on them rather. So the longer this runs, the more copper metal will form on here, the more bromine will form on here, and you'll start to see more and more discoloration. If you were to take a breath of the side over here, it will smell like chlorine gas, because that's what bromine smells like, and so you would be able to detect that. But you can take my word for it. So our first type, as you just saw, is when we have just a simple binary salt solution, and we do an electrolysis of that salt solution. And this one is very simple from kind of an overview perspective. This is just going to simply make the elements of that binary salt. So copper 2 bromide, run electricity through it, you'll produce copper, and you'll produce bromine. Now I also want to go through and show you that what happens at each end. So in this particular case, we have two things happening. This salt solution starts off as copper 2+ ions and bromide ions. And the copper 2+ ions will combine with 2 electrons to form copper atoms. So we'll turn the copper ions into copper metal. And that will be a reduction that will occur on the cathode end of things. The bromide will become bromine liquid. And so 2 bromide ions will turn into bromine and 2 electrons. And so we can, of course, combine these two reactions, canceling the 2 electrons to produce our net ionic equation. That would be like what we started with up there. These are very simple because you're just turning the things into the elements, and so these, we don't really need a ton of explanation until we get into the later steps into what's complicated about these. So decomposition of water, electrolysis of water, is where things are going to start to get into a little bit more detail of what's going on. Now, water, of course, will turn into hydrogen and oxygen when you run electric current through it, but that's really not the entire story. So now let's start to break this down. If we look at what happens at each end, we can see that this is much more complex than it looks. So on one end, the water turns into hydrogen gas. On the other end, the water turns into oxygen gas. And so, what we have happening here to balance these is for this one we're going to add hydroxides. And that's going to necessitate a couple of electrons. Then on this one, we're adding O2, or we're turning into O2, we need 2 of those, which means we'll need 4 H pluses, and then 4 electrons. So these are our 2 anode and cathode, the reactions that are occurring. So you'll note that we're making hydroxide on one side, and an acid on the other from that water. Now, if I go ahead and, let's go ahead and throw the voltages on there. So the voltage for this first reaction is negative 0.83 volts. And the voltage for this one is negative 1.23 volts. Okay, so of course we're looking at a negative overall voltage, a reaction that's not going to happen unless we force it to through some kind of battery means. If I go ahead and combine these two reactions, I need to double this top one to get my 4 electrons on both sides to cancel. So doubling that, I'll have 4 waters plus 2 more, so I'll end up with 6 total water molecules. And then I'll end up with 2 H2s and 4 hydroxides. And then I'll have my 4 H pluses from down here and my O2. Now, 4 OH minuses and 4 H pluses, these combine to make 4 waters. So we can get rid of those and replace it with 4 waters, which that will then cancel out 4 of these waters, reducing it down to 2. So when I combine these two half reactions, I end up with 2 water becomes 2 hydrogen and an oxygen, which is my original equation. Now the voltages on these are going to become critical when we get into the third type, which is a mix of the first and the second. Sometimes we'll get where one of these half reactions will occur and the other one will not. So here we're going to do some electrolysis of sodium iodide. And before we start, we're going to take a little bit of phenolphthalein on each end. Then we're going to hook up our electrodes. And a little more phenolphthalein to get some contact. So you're going to see two things happening. One is that we're going to end up making some bubbles here with some hydroxide. So let's zoom in really well. So you can see the hydrogen gas being evolved, and you can see the pink color indicating that we're making hydroxide. At the other one we're making iodine, which is pretty difficult to see. It's kind of a brownish when it's dissolved in water. So our third type of reaction is when we have some of both occurring. So in this we're going to see either a cation or an anion do a typical reduction or oxidation, and then the other part is not going to be able to react, rather the water is going to participate in the reaction. So here we have sodium iodide. The iodide will turn into iodine. Really straightforward half reaction. There's our oxidation. The sodium, on the other hand, though, we have a problem. So if the sodium were to react with the electron and produce sodium metal, you have to understand that that's taking place in water. And that's a problem because this sodium would immediately react with the water to produce sodium hydroxide and hydrogen gas. And so what's actually going to happen is that the water is going to be participating in the reaction to form hydroxide and hydrogen gas rather than the sodium. Now for the voltages behind these, the iodide turning into iodine has a voltage of negative 0.54 volts, which is less negative than the water reaction where water is turned into oxygen gas. The sodium, if this reaction were to occur right here, negative 2.71 volts would be required. So in order for that to work, we need to apply 2.71 volts for that to happen. However, the water component turning into these, this half reaction has a voltage of negative 0.83. So we can see that this is a much more desirable reaction from the sense that it's easier for this to occur. Even if this by chance does happen to occur, we're applying some very large voltage and we produce this, that's then going to react with the water of its own volition and we'll end up producing this anyways. So what's going to happen here is we're actually going to do the reaction. We're going to end up with this reaction occurring and our water turning into hydroxide and hydrogen. And so we're going to have two different things happen at both ends. Now, if we go ahead and rewrite this, we will have two iodides turning into iodine. And then we will have our water half reaction, which would be two of these plus two electrons becoming hydroxide, hydrogen gas, like that. So this is going to be what our reaction is. We can then combine these to form this. Two iodides plus two waters turns into iodine, two hydroxides, and hydrogen gas. So this is an example where the iodide is reacting, but then the sodium is not capable of reacting, or if it does react, is going to cause this to react in its place. And so the water ends up being reduced to hydrogen gas, the iodide ends up being oxidized to iodide. Now to figure out when this is going to happen, we use those redox potentials. So what I would need to do is I would need to compare the voltage of this, which is minus 0.83 volts, and then compare that to the sodium, which was minus 2.71. This is obviously a more favorable voltage than minus 2.7. And so this is going to be the reaction that occurs. If I do that with this, the voltage on the iodide is negative 0.54 volts, whereas the water turning into oxygen gas had a voltage of negative 1.23. So in that case, this is favorable to the water being oxidized, but the water being reduced is favorable to the sodium being reduced. And that's how you would compare whether reaction type 1, 2, or 3 would occur, by using your redox potentials for the water half reactions compared to what half reactions you would have occur for the pure chemical. Now if I didn't do this in water, if I just had sodium iodide that was molten, then I would end up producing sodium metal and iodine on the other end of that. Okay? So those are the three different ways you're going to experience some electrolysis reaction, and you're either going to have the salt component oxidize and reduce, or you're going to have the water oxidized and reduced, or you're going to have one from each.